Hello students, I am Vivek Kumar Gupta, Assistant Professor at IIMT College of Science and Technology, Greater Noida. In this lecture, we will discuss about the numerical integration. Okay. So let's first discuss about the what are the outlines or what we are going to discuss in this lecture series. Okay. So these outlines of today's lecture is first we will discuss about the different integrals, lower and upper sums in the case of Riemann integration or Riemann sums, and two different methodologies for the numerical integration which are used for the uniformly spaced samples. First is the trapezoid rules and other is central rules. Okay. So what is integration? In class 12th calculus, in the class 12th calculus, we have already studied about the integration and its application. As we know that integration is the inverse process of differentiation. Differentiation is used to measure the rate of change, but integration, which is inverse process of differentiation, which is used to find the area under the curve. In the process of measuring of the area under the curve is given by the I is equal to a to b fx dx. Here we can see that fx is a curve which is plotted by the, which is plotted, and the black region or the area under the curve under the limit, where a is the lower limit of integration and b is the upper limit of integration. So there are some other for the function to be integrable. There are some conditions. There must be condition fulfilled. That condition must be fulfilled. First of all, function must be continuous in the given interval. So fx must be continuous from a to b, or the closed interval in between a to b, and also fx is must be derivative of some function, capital Fx, which is called the antiderivative. Then we can find the area under the given or we can find the integration of that function. Okay. So the basic definition of integration, or what, as we have discussed, that integration between the limit f(x) dx is, which is will give the area, which is the basic definition of integral. Also, if we use the double integral, which is defined as a volume for the, which is defined as a volume for the double integration is used to define a double integration is used to define volume. Okay. So what are the methodologies to use to find this area? How we can find an integration by by some analytical techniques. To find an area, we are using to approximate the area under curve by using rectangles. So at first we divide the intervals AB, which is AB. Suppose upper lower limit to upper limit into equally spaced rectangles. So here width of each rectangle is denoted by del x, and height is to be found as the midpoint. Suppose we take the midpoint from first rectangle, which is defined as a dotted point, and function value at that dotted point will suppose x0, x1, xk are the midpoints of each rectangles. So function value as this point will produce the height of the given rectangle. So as we know that area of rectangle is length into width. So width is given by del x, and height will be given by the function value at the midpoint of the uh, function, midpoint of this rectangular width. Okay, which is also called the midpoint rule. So area under the curve can be approximated by using the sum of area of each rectangle. Okay. So here we have defined fxk. Fxk is the height of the rectangle, and del x is the width of that rectangle. So suppose x1, x2, xk are the different points of the midpoints of the each rectangle. So adding those area will produce the equivalent or approximate area of the curve. So limit n tending to infinity. What does it mean by limit n tending to infinity? So we can partition the equal intervals, the A to B interval in infinite symbol in how as we required number of rectangles. Okay, so n can be large, n can be whatever the choice. Okay, here. So del x, how we divide the over intervals a to b in equally spaced. So we can divide length of the intervals divided by n. N is the required number of rectangles we wanted. So del x can be found is equal to b minus a upon n. Okay. So simply we can say that area of the fx dx or a to b is equal to sum of height into width. Okay. So by using midpoint rule or the integration, these are the motivation we can find our equivalent. So what are the motivation for the other numerical integration method? So let me explain. So first is we can find or evaluate the integral I a to b fx ds without doing the calculation analytically necessarily. And in other case, suppose an integration is given which are continuous. Here we can see that fx is 0 to 2 plus cos 1 plus root x and root 1 plus 0.5x is a continuous function because we know that our rational function fx upon gx is continuous where gx is not equal to 0 when fx and gx both are continuous. Here fx is 2 plus cos x. This is a continuous function, cos is continuous function, and 2 is a constant, so addition of two continuous function is also continuous. And root under 1 plus 0.5x is also continuous. So using the rational function of continuous rational theorem of continuous function is can say that this function is continuous. But analytically, finding the area between in the interval 0 to 2 is very difficult. So we will use the different method. Okay. So another method is Riemann integral theorem. So what is Riemann integral theorem? As we know that integration is a summing process. Thus virtually all numerical approximation can be represented by I is equal to a to b fx dx is equal to summation from I is equal to 1 to n wi fxi plus et. Here we can see that during approximation of the area under curve by using rectangles, we can see that some of the area of rectangle are outside the curve of the function. And some places are blank which are not covered by the rectangle. So we can see that these places are producing an error under the area under the curve, which are not giving the exact value. So which is denoted the error which are in the area which is denoted by EP, in which WI are the widths of the rectangle, XI are the sampling points, and ET is the truncation. And we have already discussed that area can be found for any valid function that is continuous on the closed and bounded interval of the integration. So the partitioning of the integral. So the most common numerical integration formula is based on equally spaced data points. So that means with the given lower limit to upper limit, we divide the intervals into n intervals and can be written in this form. So suppose x0 to xn fx dx is equal to also can be written as x0 to x1, x1 to x2, and xn minus n to xn. And in each interval will integrate the function fx dx. So let me show the picture of what is use of upper sums. And so suppose if you wanted to approximate more refinedly an area under the curve, we'll take the rectangle which is which will mostly cover the whole rectangle. Okay, so there will be two types of rectangle. First of that which will be outside the curve, and second will be inside rectangle. So there will be there will be two scenarios generated in this situation. So we'll do two types of integration. So here we can see that if we use the upper limit of upper height of the rectangle and the lower height of the rectangle, we can say that the area under the curve is in between area of these two. So lower subs or lower part of these rectangles will produce the lesser amount of the area, but upper rectangle will produce the exact more or extreme for the area under the curve. So exact area of under the curve will be lie between in these two. So let's define of the what is the upper sum. So here we consider the fx is greater than 0 everywhere in the interval a to b, or the given intervals where we have to find the integration. If within each interval we could determine the maximum value of the function, then we have x0 to xn fx dx. Fx mi is the supremum of the function in that given interval. So suppose x0 to x1 is the first interval, so m will be the maximum value for this interval of function's maximum value, which will be represented by mi, which is also called the supremum. Okay. So the difference will produce the width. So x1 minus x0 will produce x1 minus x0 will produce the width of this rectangle, and mi will produce the height of the rectangle. Summing those will find the area which is greater than the exact value, exact area of the function. Okay. Now similarly we can define the lower sum. Likewise, still assuming that fx is greater than 0 everywhere, within each interval we can determine the minimum value of the function. Then we have x0 to xn fx dfx, and summation from i0 to n minus 1. Mi is the infimum. Infimum means the lower value of the rectangle. Okay, so by seeing this picture, we can say that area of the exact under the curve, under the function or under the given function curve will be in between the upper sums area or lower sums area. So we can define now. We can now define. We now have a bound on the integral of the function for some partition x0 to xn. As n tending to infinity, one would assume that the sum of the upper lower bounds and the lower sum of the lower bounds approach each other. You can see that by using the intervals. So in these intervals, we can say that the difference between the lower sum area and upper sum area is very high. But dividing the rectangles into final parts, we can say that that will be minimized. And as we divide each intervals in more finer terms or in more number of rectangles, the difference between the upper integrals, upper sum area to lower sum area is going to minimize. So in these three pictures, we can see that graphically that the difference between the upper sum area to the lower sum area is reducing by as we increasing the number of partitions. Okay. So this is the case for most function, and we call these Riemann integrable function. So we can here we can see that area of the function x0 to xn is is lying between lower sum area to is greater than lower sum area and lesser than the upper sum. Okay. So this is the Riemann integration method to find an area or to find an integration, definite integration for a function. Now we can use here in earlier method we have used the rectangular region to find out the area. Now we can see that using a trapezoid, which can be more approximated or more accurate to approximate a curve, and which will produce a lesser amount of error rather than the rectangle. So by looking at this picture, we can see that by using trapezoid, which will be producing a very less amount of error for the given function rather than the rectangle. So the trapezoidal rule for estimating definite integrals uses trapezoids. So as name suggests, so trapezoids will produce trapezoidal rule rather than rectangles to approximate the area under a curve. To gain insight into the final form of the rule, consider the trapezoids shown in figure. We assume that the length of each subinterval is given by Lx. So we are discussing the trapezoid rules which are of equal intervals, or which will call the which is the equal length of we are dividing the partition into equal subintervals. So each length from x1 minus x0 will find, that is del x, x2 minus x1 is also del x, x3 minus x2 is also del x, and x4 minus x3 is del x. So each are divided into equal subintervals, okay, which is shown in the figure. As we know that area of the trapezoid, area of trapezoid we can find by using the formula half into h into b1 plus b2, where h is the height and b1 plus b2 is the basis of length of b1 and trapezoid. So this will be b1 and b2, and height will be the difference between these two, okay, which is also good. So here in this case, h is equal to del x, and b1 is equal to value of function at x0 and function of x0. So by using this, we can derive the formula for the trapezoidal rules. So we say that the first trapezoidal has a length del x, parallel basis of length fx0 and fx1. Thus the area of the trapezoid, first trapezoid figure is half del x fx0 plus fx1. The areas of the remaining three trapezoids are produced similarly, half h del x fx1 plus fx2, and similarly del x h2 half fx2 plus fx3. Consequently, to find the area under the curve, we have to add all those area. So we have added all those area of trapezoids, which will be produce approximated result. Since it is an approximation, because you can see that there are some area which is left out from into the curve, which are not covered using the trapezoids, and there are some area which are overly overlapped, yeah, outside the function, outside the curve of the function. Okay. So which will produce an error to the given function. So area under the curve a to b fx dx will be given by the sum of these trapezoids. Then we can see that we can take common del x half and add the similar terms. So after taking out a common factor of del x and combining like terms, we have area from a to b fx dx, which is half del x fx0 to fx1 plus 2 fx2 plus 2 fx3 and plus fx1. Okay. So in this figure, to find out the formula for trapezoidal rule, we have uses only 4 partitions, but it can be generalized to the n number of partitions. So general formula or general statement for the trapezoidal rule is can be written as the form. Assume that fx is continuous over closed interval ab. Let n be a Poisson integer, and del x is equal to b minus a upon n. So del x will be del x is can be found for the length of the trapezoids we find by B minus A upon N is the number of trapezoids we wanted to find out. Let AB be divided into n subintervals, each of length Lx with endpoints at P, x0, x1, x2, etc. Then area integration from A to B fx dx will be approximated by half del x fx0 plus 2 fx1 plus 2 fx2 plus 2 fx3. So trapezoidal roots. So since we have discussed that it has some error which can be approximated by the given formula, and whose order is h cube. Okay. So error of the trapezoidal rule is given by negative of 4.12 at double dash chi h cube, where h is equal to b minus a, and chi is the an unknown point between a to b, which can be found out by using so error can be zero when double derivative of function will be zero. Okay. Since h cannot be zero, h is the difference between the upper limit and lower limit. If h is equal to zero, there is no meaning to finding the integration. Okay. So f double dash can be zero at any point xi, which is in between the interval a to b. Okay. Let's do some example to find out the integral. So here we are given a function fx is equal to power negative x square. As we can see that exponential function of continuous, and it is defined under the value of is under the interval 0 to 2. So from using trapezoidal rule 0 to 2, we can find the integration, the approximate integration, which is 0 from integration from 0 to 2 e to the power negative x square. So formula is b minus a by 2 f plus. Since we are not using any partition, here the only partition is, so the integration is given by this. Okay. And the estimate can be found out by using the formula e to minus 1 by 12 double dash I h cube. H is equal to b minus a, and it xi is the point between a to b. So xi is an unknown point. Here we using xi as a reference value. Okay. So double derivative of e to the power negative square is given by this, and my value for f0 point at the point 0 is equal to and about 2. So the average value will be given by this. Okay. So we have calculated the error for this function is 0.5. So similarly for the we can if you use the more number of intervals, it will produce better result, and the error will be in the square root. Okay. So by picture we can see that suppose if we have using only two number of trapezoids, then which will be, you can see that there are very much of area under the curve is left out from the trapezoids. Okay. So if increase trapezoids are also can be said that a linear function. Linearly we can using a linear function we can approximate. So using n is equal to 3, we can say that we can see that much of the area of under the curve is covered during using more number of intervals. Okay. Similarly, increasing the number of intervals, we can cover more and more of the area under curve, which will produce a better result for the area under curve, or which will produce the very better result for the definite integral. Now the another method which is called Simpson rule. So Simpson rule are categorized into two methods. First is Simpson 1/3 rule, and another is Simpson 3/8. So with the midpoint rule, one can estimate area of region under the curve by using rectangles. In essence, approximate the curve with piecewise constant function. So in the starting case, we have discussed midwise point. So this is the first where we have to find the midpoint of the function value x0 to x1 and the function value at that point which will produce the height and the difference is with the width. So let which will produce the area of rectangle which is called the midpoint. So with the midpoint rule, one can estimate areas of region under curve by using rectangles. In a sense, approximate the area uh, by using rectangles. With piecewise constant function. With the trapezoidal rule, we approximate the curve by using piecewise linear function. As we can see that in this picture, trapezoidal are drawn as a linear function. Okay. So we have approximated in the trapezoidal case, we have approximated the function by using piecewise linear function. Or it also we can see in the derivation, we have used only a linear function to approximate our. There is no quadratic or square terms, so only a linear terms are written in the. So we have approximated the curve by using by in the case of trapezoidal by using piecewise linear function. So what if we instead to approximate the curve using piecewise quadratic function? With Simpson rule, we do just this. We partition the interval into an even number of subintervals and each of equal width. Here we have discussing two or three methods. First is the midpoint rule, another is trapezoidal rule and Simpson rule. All are using equal width of intervals. So let's understand the picture diagram. In case of first, we are partition to only two intervals. So to estimate a quadratic equation, we need 3 points. So 3 points are x0, x1, and x2. But in this case, it is overestimated the our given function or the area under the area of the curve, which overestimated by the given polynomial. But as we have increased the number of partition, there are two polynomials, two particular polynomials p1x and p2x, which are estimated exactly of the given function. So this is more refined and more has less error other than trapezoidal method or rectangular. So let's find out how we can derive the sunset method. So trapezoidal rule was based on approximating the integrand by first order polynomial, that is a linear function, and then integrating the polynomial in the interval of integration. Simpson, other than Simpson third rule is an extension of trapezoidal rule, where the integrand is approximated by a second order. Hence, I is equal to integration into the fx dx integration is approximated by f2x, which is a quadratic second order polynomial or a quadratic polynomial. So to estimate second order polynomial, there are three parameters a0, a1, a2, which are unknown. So we have to estimate these 3 points a0, a1, a2 by using the given value of the function of interval. So we have to choose at least 3 points of the intervals. Or we have to choose at least two partition, two intervals to find out these three values. So we have taken two partition a to a plus b by 2 and b, and the function value of these 3 points. A plus b by 2 is the midpoint between a and b. As the 3 points of the function to evaluate a0, a1, and a2. So we find out the function value at fa, a plus b, and b. So f2a is equal to given by this f2 the point and add to B at the point B. Okay. Solving the previous equation for A0, A1, A2 gives A0, A1, A2 in terms of A, B and A plus B by 2 and the function value of these two. So now we have to integrate f to x dx at A0 plus A1x, which is A0 plus A1x plus A2x square dx. By integrating and putting the limit, we'll find these values. Here A0, A1, A2 are the unknown parameters. We have to substitute the value in terms of A, B and midpoint of the function value. Substituting values of A0, A1, A2 gives this equation. So, which is B minus A 6 F plus 4 into midpoint of the value plus F. Since for our Simpson one-third rule, the interval AB is broken into two segments. The segment width is H is equal to B minus A. As A to B F to X dx is equal to H by 3 plus 2 F plus B by 2 plus F. Because the above form has one-third in its formula, that's why it is called Simpson one-third rule. Let's do an example and find out the error. And the absolute error and absolute relative to error. So the distance covered by a rocket from t is equal to 3, t is equal to 13 is given by this formula. Okay. So exact integrating these we will find the x is equal to this, and the exact value of the integration is given by this integration. So the true error is, we know that can be find out by the exact value minus approximated value. So this is exact value and this is the approximated using the Simpson rule. The difference is this is our true error. And the absolute error will be given by the true error divided by exact value. So absolute error is 0.0396%. The Simpson one-third rule can be approximated using the Lagrange's polynomial whenever we have given the tabulated value. Suppose we have n number of values are given in function value at the endpoint. So we'll first approximate the polynomial using the Lagrange's interpolation method for unequal space value. Since Lagrange interpolation method is used to unequal spaced value, quite okay. So by using this formula, we can also estimate the Simpson one-third rule, right? Which will produce a quantic polynomial. Now, Simpson one-third 3-8 rule needs 3 intervals and 4 data points, which will be given by the cubic by using a cubic polynomial. Okay, and the which will be the Simpson one-third 3-8 rule is defined as divide h fx0 plus 3x1 plus 3fx2 plus 3fx3. So here 3fx1 will be given, and h is going to be given by b minus f1. So error is same order as 1/3 rule, and error is given by minus 3 by 80 s to the power 5 f to the 4 is high, and its order is s to the power 3. So let's do comparison between Simpson one-third and Simpson 3/8. So Simpson one-third rule and Simpson 3/8 rule have the same order of error, that is s to the power 4. But for the trapezoidal rule, has an error of h square. Okay. So h is how as we know that h is how we are finding h. So b minus a upon 3. If we are dividing three equal intervals, if the number of intervals are increasing, h will be a smaller value. So it depends upon how much of partition we are finding. So if h is a very small number, so the fourth order of h is also small compared to h square. That's why Simpson rule has lesser error than the trapezoidal. Let me repeat again. So H is defined as B minus A upon N. So N is the number of partitions, whatever we need. So if we increase the number of partitions, the value of H will be smaller. So the power of smaller value, fourth power of smaller value will be more smaller than the square value of square of that. So trapezoidal rule has greater error than the Simpson. Okay. Simpson 1/3 rule requires even number of segments, and Simpson 3/8 rule requires multiple of 3 segments. Both Simpson method require evenly spaced data. Now, summary of this lecture is what we have discussed in this lecture. So we can use numerical integration to estimate the value of definite integrals when a closed form of the integral is difficult to find, or when an approximate value only of the different integral is needed. Okay, this is our first point. The second point is in the case of numerical integration, the most commonly used techniques are we have discussed as the midpoint rule, trapezoidal rule, and Simpson. And Simpson rule has two types. First one Simpson 1/3 rule, and another is Simpson 3/8. The midpoint rule approximates the different integral using rectangular regions, whereas the trapezoidal approximate the different integrals using trapezoidals. But in the case of Simpson rule, the approximation, the different integrals are first approximating the original function using piecewise quadratic. Or also we can use the cubic polynomial. Okay. Thank you.